Hi everyone, and welcome to our presentation. My name is Carsten Michel. I'm working as a senior expert in network engineering at Deutsche Telekom. For those of you not familiar with Deutsche Telekom, we are the largest service provider in Germany and one of the biggest in Europe. Today I will give you some insights into the project Access 4.0, which is the first project using disaggregated routing and BNG system within Deutsche Telekom. I do this presentation together with Hannes Gredler from our collaboration partner RT-Brick. So our journey into disaggregation at Deutsche Telekom started a couple of years back when some people of our architecture team investigated the AT&T's CORD approach. CORD stands for Central Office Re-Architecture as a Data Center. And as the name implies, the basic idea of CORD is to replace an existing black box in the access and aggregation network with bare metal servers and bare metal switches and run open software on top of it. For us, CORD was the starting point. We have developed our own solution, which meets our requirements, fits into our existing network, and also fits in our existing OSS and BSS systems. For example, CORD has a centralized SDN approach using OpenFlow. However, in our network, we have a huge amount of network states, which we cannot easily get rid of, and which are difficult to handle with centralized SDN concepts. Therefore, we built a hybrid SDN solution. Today, our network consists of roughly 1,000 points of presence across Germany. In these points of presence, we block network gateways, BNGs for some time, to terminate customer traffic, which is mainly IP over PVPoE. Customers being residential customers as well as business customers on the same platform. The main aim for Access 4.0 project is to provide high-speed internet services with triple play support, but also business services in the future. And in order to provide this in a very cost-efficient way, and also preventing vendor lock-ins, we've decided to disaggregate software and hardware. Our goal is to get an open architecture which allows us to replace any component at any time, and also allows us to integrate these components easily into our IT landscape. Therefore, we've built a disaggregated BNG solution together with RT-Brick, which is now live in our production network. We are highly looking for collaboration in the service provider community, especially with other ISPs in Europe and in the US, which have similar ideas and similar needs as we have. We've also contributed some of our work already to standardization groups, as you can see on the slide, and we will continue to do so.
My name is Hannes Gredler. I'm the CTO and co-founder of RT-Brick. Starting about in 2012, I've witnessed data center operators to transition their sourcing strategy away from integrated systems towards bare metal switches plus a disaggregated NOS, mostly to get back flexibility and cost savings. Along with the proliferation of merchant silicon, we have seen many networking operating systems, mostly around a DC data center feature set, but none really targeted to a classical telco footprint. Therefore, I wanted to close that gap and founded the company together with my co-founder, Praveen Bandakar, who was my product manager at Juniper Networks. RT-Brick and Deutsche Telekom paths have intersected in 2017 with an interesting problem to solve. DT have deployed thousands of chassis-based routers. If you zoom inside the box, you'll see core-facing line cards, customer-facing line cards, all interconnected via fabric cards. The cards pass traffic using a proprietary data plane protocol, and the line cards are getting programmed using a proprietary control protocol. Now, the problem with this setup is that there is no uniform compatibility layer both for the data plane and the control plane. Of course, you cannot combine a line card of vendor A with a line card from vendor B. Worse, you often cannot combine line card version 1 from vendor A with line card version 2 from vendor A. And this typically requires ongoing forklift upgrades during the life cycle of the equipment. And in fact, there is several hardware teams who swap components every single day. So what we did is to create essentially a discrete version of that integrated router. The proprietary fabric protocol has been replaced with Ethernet, MPLS segment routing, and the control plane has been replaced with BGP labeled unicast plus segment routing extension for the underlay, and BGP L3 VPN and BGP MVPN for the overlay. On the management plane, we ensure that each of our smaller switches has a local x86-based board with all the local protocol support to run autonomously if there is, let's say, loss of connectivity to the SDN controller. Yet, as you see, there is a controller who provides high-level instructions, which I'm talking about in 2 slides from now.
Okay, in the very beginning, we had a look at a completely virtualized BNG solution, but found out that running these kinds of services on standard data center servers does not really meet our requirements, especially not in terms of QoS support and power consumption. Therefore, we started with an off-the-shelf switch because we believe that we need a dedicated data plane component. We also spent some time investigating different types and different vendors of merchant silicon, and we still do so. As of now, we've decided to start with Broadcom's Trader DNX ASIC family because they best meet our requirements in terms of scaling. Scaling means route scaling as well as subscriber scaling, and in terms of QoS. In Deutsche Telekom, we extensively use hierarchical QoS, which is not easy to implement with most chips on the market. Starting back in 2018, 2019, we used standard edge-core white box switches with Broadcom Qumran MX and a knowledge-based processor on board. The Qumran MX chip provides a sophisticated traffic manager that allows us to implement our hierarchical QoS schema. The Qumran MX also provides enough throughput for our use cases, and the FIP size is sufficient for most internet applications. In addition, the knowledge-based processor is used for lookup table extension to support a large number of match rules that we need, for instance, for subscriber access lists, statistics counters, service queues, etc. Currently, we are looking into the next generation of switches with higher port density. We are actively working with some OEM vendors on the design of these switches, which will be based on Broadcom Qumran 2C silicon. The increased performance of this ASIC allows us to implement the routing stuff, including all the services we've planned so far, without any KBP, at least not on the spine switches. For the leaf switches, we are still investigating if a next generation KBP is necessary or not. Again, we do not want to have hardware which is specifically built for Deutsche Telekom only. We are looking for commodity hardware to split the development costs across a larger group of interesting carriers. Let's have a look how the network design looks like in more detail. First of all, we do not have a greenfield environment at Deutsche Telekom. We cannot really start from the scratch. We have neighboring systems which we need to connect with. The basic access for the row pod consists of spine and leaf switches. Traditional data centers normally use 3-stage glass fabrics because they have a huge amount of traffic which is flowing from east to west. However, in a telco environment, the majority of traffic flows from north to south. And in order to reduce the number of switches, and of course the costs, In our setup, the border leaf switches have been removed from the topology and collapsed with the spine switches into a single device, therefore resulting in a two-stage fabric. On the core facing side, there's the IP/MPLS backbone network speaking standard routing protocols like ISIS and BGP. The spine switches are fully integrated into our backbone network as PE routers, holding the entire BGP routing table. On the other side, customers are connected via MSANs, OLTs, or whatever access equipment, usually establishing PPPoE sessions to one of our leaf switches. There's also the need to provide layer 2 and layer 3 bitstream access for other ISPs. In addition, we use standard protocols like radios for session authentication and accounting. Between the leaf switches and the spine switches, as Hannes already pointed out, we are relying on standard routing protocols, avoiding any proprietary fabric protocols or vendor lock-ins. All of these protocols need to be supported in the network operating system, of course. That's clear. And last but not least, we have a controller in our pod, which we call POW. This controller is running on a Kubernetes cluster, which provides services like orchestration, telemetry, data analysis, and also some kind of traffic steering. Communication is done again by standard protocols like REST or gRPC or other similar protocols.
Carsten has earlier alluded to that we started with the classical chord approach, and chord really means that you have a sort of a controller who micromanages each and every flow. Now, when we actually did the math and said, hey, on some of the larger central offices with potential hundred thousands of subscribers, and further assuming that for some of those services you have to program up to 80 forwarding related actions, we could not really envision how to size the controller properly to manage that load. So therefore, we have looked into a way how to fuse together what a central controller really provides of information, along with what routing protocols dynamically do discover. On the core-facing side, no big surprise here, BGP and ISIS running. On the fabric side, BGP LU as an underlay, L3 VPN as the overlay. And up to this point, it actually looks like an almost classic setup, like it has been deployed for the past 2 decades. Where it is actually different is the controller may influence a piece, a particular table here at the leaf, which we call the service selection table, where we have a couple of qualifiers and also a couple of actions available. And the SDN controller can tell exactly what to do with any given customer flow. So for example, we could say, hey, please terminate VLAN 100, VLAN 200 on interface X, and please, I know from OSS that this is a residential customer, so decapsulate PPPoE and do a route lookup in the internet WRF. So this is the kind of functionality that is available to the service selection gateway. We have also made it easier for application developers, for the crew who programs the POW, our controller, to basically install remote state information, like, for example, if you terminate a service and you want to just shunt it off using an MPLS pseudowire, you do not really need to set up the underlay and everything along that path. You just need on both ends of the pseudowire tell, hey, I want to relay here a certain VLAN stack over a particular MPLS service label, and by the way, this is going to get terminated at egress router with a certain IP address. The system then combines that with the information that have been discovered by the dynamic routing protocols and fuses together the service-related information from the controller with what decentralized leaves and spines have computed.
Before we moving into some more implementation-specific details, I want to briefly touch the bring-up of the fabric network switches. An important aspect of the Access 4.0 project is to automate as much as possible. All the pods look very much the same inside. Also, they might look differently from the outside world, but internally they look completely identical using predefined addressing schema based on private IPv6 addresses and private 4-byte AS numbers. The first step of the bring-up process is to automatically provide an IP address for management, provide software images, and provide a basic configuration that allows us to build the underlay network. No surprise, we're using DHCP to get all this information to the box. But instead of using MAC addresses, which can easily be forged, we are using serial numbers to authenticate the device. The serial number of the box is stored in a database as part of the blending process. And once the switch is physically installed, the on-site engineer scans the barcode, and the POW, which I already talked about, then associates the switch with the right location and the right function. The switch is usually delivered with nothing else but an ONI installed on it. ONI stands for Open Network Install Environment, and basically is a small Linux system that provides tools to automatically install a network operating system on a bare metal switch. The ONI includes a DHCP client to initially retrieve this IP address for management. And the DHCP reply message also includes a link to the download location for the correct software. In our case, the RTPIC full stack software. The ONI takes care of the software installation process and afterwards automatically reboots the switch without any further interaction. Once the switch is rebooted, again, it gets a management IP address via DHCP, and also gets a link to download the configuration file, which will be retrieved and activated. And the nice thing about this approach is that we basically can include every white box switch into our network that supports ONI and has ONI pre-installed. The configuration file itself is also automatically provided. We have a configuration template for each switch role, in this case for the spine switches and for the leaf switches. And this template is more or less a JSON file with some variables which can be filled. These variables are device specific and either get filled by planning data, like for instance loopback addresses or so, or they get sometimes also calculated from a given algorithm. So we have a predefined schema where we calculate certain variables from. We have a template engine that uses this basic template and fills all the required data and then provides this configuration to our ZTP server ready for download by the switches. This template engine, which does all the magic, is developed by Deutsche Telekom itself. However, the information needed to get the underlying network running is very little, as we will see in the next slide. Okay, so let's have a look at the fabric underlay. The underlay network consists of spine and leaf switches. Separating underlay from overlay services is very important for us because it provides the possibility for multi-tenancy. As an incumbent, we at Deutsche Telekom are forced by regulation to provide some kind of access to other ISPs. So having a separation of overlay and underlays in our infrastructure is very critical. The leaf switches are connected to all the spine switches with a symmetric number of links, allowing equal cost multipath routing. Within the fabric itself, only external BGP is used as a control plane protocol. We are using MPLS as data plane encapsulation. The signaling is done via standard segment routing extensions to BGP. We have no need for any IGP protocol within the fabric. So usually IGPs are known for topology discovery, but in a spine leaf fabric, the topology is more or less known, so we can avoid this and can rely on BGP only. All the leaf switches have their own private AS number, while the spine switches share a single AS number. You might be already familiar with this kind of design, so this is nothing special. In order to get the underlay routing running, each switch needs a unique identifier, for instance, for the loopback address. So we have unique IDs for example, 11, 12 for the spine switches and 21, 22 for the leaf switches. We are not restricted to 2 spine switches, by the way. We can have even more, so no problem here. From this ID, we calculate all the other parameters for the underlay. For instance, the AS number, the loopback addresses, the segment routing node sits, and also various addresses for communication to the Kubernetes cluster I've already mentioned. For example, to communicate with the telemetry and the orchestrator and so on. The interesting part is the link between the switches. The links between spine and leaf switches only have an IPv6 link local address, so no need to do any configuration here. And once the leaf switch has been configured and the link between the leaf switch and the spine switch goes physically up, the leaf switch tries to establish an eBGP session to the spine switch across the IPv6 link local address. This is an event-based service implemented to overcome the lack of auto-discovery in standard BGP. The spine switches are configured to accept BGP sessions from a predefined range of AS numbers, and for authentication, the TCP authentication option is used. Once the underlay is established, everything else is run as an MPLS service on top of it. For example, standard layer 3 VPNs or layer 2 VPNs or eVPN. This is mainly done to provide multi-tenancy, as already mentioned. But it also provides a great deal of flexibility because we can easily support any new services by introducing appropriate BGP address families without changing the underlay at all. Let's consider our standard internet service as an example. This service is run as a dual stack layer 3 VPN across the fabric. The service signaling is done via BGP VPN v4 and VPN v6 address families. Remember, the next hop are labeled IPv6 addresses, as explained in the previous slide. The spine switches will handle all the routing needed for fabric internal communication, as well as communication to the backbone network. So the spine switches will have the full internet routing table within the internet VRF. The leaf switches, on the other hand, will have all the PPP subscriber-related routing information. This includes usually 3 addresses or 3 prefixes, 1/42 IPv4 prefix, 1/64 IPv6 prefix, and a delegated prefix per subscriber. In order to reduce the load and also prevent routing flaps, leaf switches will only advertise pool prefixes to the spines and hide all the subscriber-specific details. On the other hand, the spine switches will only advertise default routes to the leaf switches, as the leaf switches know that they only have upstream connectivity through the spine switches anyway. So let's have a look at the backbone connectivity. The spine switches are physically connected to our P routers, LSRs, of the IP MPLS network. The internet service runs on the spine switches as a kind of MPLS layer 3 VPN. This implies that all the backbone-facing protocols run as PEC routing protocols within the internet VPN instance. The IP/MPLS backbone network delivers its service based on BGP over IPv4. Internet BGP sessions are established to multiple route reflectors for redundancy. Services include IPv4 Internet, IPv6 Internet, which is implemented as 6PE service, as well as traditional Layer 2 and Layer 3 VPNs. For the MPLS transport, ISS level 1 routing is used to connect to the LSRs. Label distribution is done via segment routing extensions. We have used LDP in the past, but with this project, we're only using segment routing. This is kind of tricky, as there are not many implementations on the market that support running labeled ISIS as a PEC routing protocol. One thing to highlight is that in order to reduce the number of segment routing node sits in the backbone network, the spine switches share an Anycast node sit, which is advertised to the core network and which is used as a BGP next hop for all the BGP MPLS services. This has also the benefit that we can scale to more than 2 switches without increasing the load in the IP/MPLS backbone, as they just appear as a single device from an ISIS perspective. We've already explained that everything in the fabric is implemented as a service. So multicast, which is used for IPTV, is just another example for such a service. Because we are substituting a black box BNG device, we cannot change any interface that is outside the fabric. So customers still signal their interest in receiving a specific multicast channel via IGMP version 2 to the leaf switches. IGMP version 2 requests, by the way, are sent within an existing PPP session, so no separate channel here. On the other side, the backbone network uses PIM to signal multicast today, maybe MLDP in the future. Within the fabric, multicast is implemented as a next generation MVPN service. Again, you see the pattern. We are relying on the BGP protocol. The leaf switches convert the IGMP joins to specific multicast and send BGP source join messages towards the spine switches, which themselves convert these messages to the protocol used in the backbone. As we have only one hierarchy of leaf switches, the spine switches need to replicate the multicast traffic for each leaf switch. Setting up point-to-multipoint LSPs does not bring any benefits from a data plane perspective, but only increases the complexity of the control plane. So we've chosen to use increased replication on the spine switches for the sake of simplicity. The leaf switches will take care of the multicast replication to the individual subscribers.
So now we had the challenge of developing an entire NOS stack in support of all those protocols. And an entire NOS stack essentially means infrastructure, APIs, CLIs, data plane code, build a test harness around it, and get it production ready. How did we do it? We've started with the core idea of a distributed data store that can handle even cruel BGP workloads of hundreds of millions of BGP paths, and focused a lot on getting the transaction performance here right, up to 2 million transactions per CPU core. Since every daemon in the system needs also to share state with one another, we had to also ensure that we can utilize the maximum memory bandwidth between CPU cores, and as such, really only that memory bandwidth is the limit using shared memory sockets. You may ask yourself why we did not really start with good, popular open source backstores, for example, like Redis. And I can tell you, we looked at most of what was available at the time, but in 2016, there was no good multi-threading support for Redis, and also the clustering support was in a very early stage, mostly lacking end-to-end integrity protocol support here. Now, that ubiquitous data store concept has also fundamentally changed how we have built routing and access protocols on top of that. Think about that every protocol gets broken down to a table schema for holding its peers, adjacencies, link state databases, ribbon, ribouts, subscriber table, statistics, even logs. So everything really gets reduced to a table schema. Now, by reducing everything to a few transaction to a database and a clearly defined table schema, one can auto-generate an API and read, write every attribute in that table, and sometimes really look inside a particular protocol's implementation. That thing is not only tremendously useful for operations because nothing gets really hidden. It also helps developers, testers, and customer validation teams to build together jointly regression and validation test cases. It is fair to say that the idea of the backstore plus the auto-generated API has really established here a common language almost between the developers and also here are customers doing all the pre-qualification of the software. Now, what we have built underneath that data store is also a very large module. We call that a forwarding abstraction, forwarding hierarchy dependency manager, which is a bit of a large name. Short terminology here is RIPD and FIPD. It is essentially a standard way to expose certain primitives. Primitives like interfaces, routes, next hops, to expose slicing concepts like VRFs, virtual forwarding tables, model various tunneling protocols, MPLS, pseudowire, PPPoE, L2DP. There is also a standard abstraction for matching rules. We have mentioned service selection before. We mostly try to break that down into chip-level TCAM lookups, counters, and HCOS. What this piece of software does also, it tries to figure out and compile all the various information from various layers. So if the SDN controller has instantiated, let's say, a pseudowire, and then BGP LU has discovered a fabric route, and in order to resolve, we are relying on an ARP ND response from a neighbor, all those information we call a forwarding chain. And once a forwarding chain is ready, it is resolvable. We actually pour out individual chip-level instructions. So underneath that big gray bar, there is forwarding plugins. We've started here with FDIAO x86 code, mostly in the proof of concept phase of the company. Then later on, we have built a full BNG on Barefoot Tofino. But as Carsten has mentioned, there was a lot of emphasis on traffic management capabilities, hierarchical, HCOS, policing, shaping, all of that. And DT Network Engineering has here found the Broadcom DNX product line, particularly Jericho and Jericho 2, a good fit. Now, all of that software gets bundled in, I would say, totally now roughly 20 different daemons, which run as a systemd service inside a Linux container. The Linux container is a standard LXC 2.0 container running unchanged, almost unchanged version of Ubuntu 18.04, and our daemons, our software packages, all run in user space and are integrated in Ubuntu's packet manager. So upgrading a piece of software works exactly like you would do it on the Ubuntu server. Outside of that LXC container on the host OS, we have a small container runtime of ours, which has been built around mostly LXD 2.0. What it does is simply starting, stopping containers, loading container images, graceful shutdown and insertion of components, making sure that all the software components inside are running, so it tracks keep alive signatures, but also does, of course, handle software upgrades and downgrades. Our model is very simple. There may be several containers stored on the switch. However, only one will be running. That is usually the one that controls the forwarding hardware. The container runtime also is our universal API gateway into the container. So whatever external protocol you want to access the switch, and there's plenty of those, starting from, of course, SSH, TAC Plus for authentication, REST calls of all sorts of flavors, OAuth. So all of those things are here also implemented in the container runtime. The idea is we have just a single endpoint where we can talk mostly using standard-based protocols, even outright open source packages. The BDS data store for us is a single source of truth. We retrieve all the state in and out from the table. It is not just a standalone key value store, it is also a plugin server. So maybe you're familiar with the Redis database, able to run Lua scripts. We have added here the capability to load any particular shared library, any particular symbol. And what we can do here, and what we do is for every table that we define, we can actually define here a couple of stored procedure symbols. And if an object gets inserted in that table, that code is getting invoked. And it doesn't really matter, you know, how the element, how the object gets into the system, whether it's coming from an API or from an embedded TCP/IP stack or from our own plugin code. In fact, the whole state flow within the system is being modeled after, hey, some object gets installed in the table, and this triggers some plugin code, which again publishes and reconciles several information into another table. I have prepared here a small example that should just get you the idea how a simple route flow works in the system. Let's take, for example, a producer of routing information, like the BGP a rib-out piece of software. So usually what it does is, after learning its routing information, doing best path selection, policy, and all of that, it publishes the information in a VRF-specific table, along with, and it holds references along to a particular next hop table, which is shared across routing instances. Of course, if there is ICMP, there is also the possibility to group several next hops together in next hop sets up to 256 ECMP neighbors, whatever the local forwarding hardware does support. So now, the next component, which is the RIP manager, subscribes to those tables, reads all the FIP local tables from ISIS, BGP, even access, right? And conciles what is the best route source in case there is an overlap. Now something interesting happens, right? Now the best path or the best protocol gets selected along with a given forwarding chain. And this can be multiple levels of route resolution. And if it is possible to resolve a particular route chain, it finally ends up here in that global RIP adjacency table. Now, all the lower forwarding tables in the forwarding complex subscribe to that table and actually construct their local forwarding tables from that. So in a typical switch, we always have two. We have a hardware plugin, and we have also FDIO, which we use for sending and receiving the L3 traffic. So what we do here is for every route object, there is a local API out table, and we use those API out tables for doing very granular bookkeeping, what actually did went to, let's say, a third-party code base. So, for example, for VPP, what have been all those VPP API route calls and also the result codes. Similar thing here also on Jericho 2. Every entry in that API out table actually translates into an SDK call, and we store also the result from that. That sort of setup has really established making quick progress for hardware integration, because you can very easily troubleshoot where a certain route or next hop in the route flow got broken, because you have almost like a live log plus all the history, what has happened here. And this, again, allows for quick troubleshooting and nailing issues. The concept of a central data store also is a bit the dream of networking operation folks. One thing that we had to fix early on is the question of scaling. Now think about, let's say, Carsten has mentioned there is thousands of modular based routers, and if you break it down into disaggregated versions, one thing is certain, right? It's going to be more than one, right? So potentially there might be, 8, 9, 10,000 of individual switches. Now, how do you actually monitor those switches? How do you keep track of interesting parameters and all of that? We did not really feel comfortable by actually pulling data from up to 10,000 switches from a centralized collector infrastructure, because pulling up to 400 time series table and retaining it for an extended amount of time consumes a lot of storage, which we didn't really put a whole lot of investment in. So we thought, hey, why not really build here the telemetry solution as part of the switch OS? After all, it is a standard Ubuntu-based installation, so we can just take an open source time series database like Prometheus, and we have integrated that we can do high-frequency samples of every scalar that we have in the individual daemons in the BDS data store. And Prometheus is much more than just a scraper for a time series database. It also has a very nifty math core where you can generate, where you can derive certain sessions. So we can actually on the switch pre-produce things like, hey, let's sample the aggregate bandwidth on all the access interfaces and divide it by the number of logged in subscribers, and pass that time series further upstream and federate. So we can actually do pre-aggregation in for telemetry. And this gets me to the end of my part of this talk, and I hand it back to Carsten, which will give you a summary and wrap up.
Yeah, thanks. Wrapping up, we have managed to develop and build a disaggregated router and BNG system, and got it up and running in our production network at the end of 2020. Disaggregation of network equipment means that you have to deal with a lot more individual components than before, as Hannes already mentioned. This means that you can only do this using automation and DevOps principles, that's for sure. However, on the other side, splitting up hardware and software allows a much faster life cycle and also much faster time to market. Thanks for your attention.
Hello, thank you, Carsten and Hannes again. We have a few questions for you, and it looks like you have been active in the Q&A, answering questions as we go. So let me see what questions. Are there questions here that that you haven't answered in the chat? Or if there's any questions in here that you'd like to elaborate on. I see a question about using OEM vendors. Sorry, did you use the OEM vendors routing stack on this fabric switches or others?
Yeah, we don't. So basically, the only software component from the OEM vendor we are using is the ONE. I mean, this is an open source project, but normally the vendor has to do some slight adjustments to it, but that's the only component from the OEM vendor we're using.
Okay. Question, are you multi-homing your leafs? Looks like you've answered that in the chat, but if you'd like to elaborate.
Yes, we are using equal-cost multipath routing, so we are multi-homing the leaves equally to all the spine switches. In our case, at the moment, that's 2 spine switches, but yeah, it's okay. Equally.
Okay. And a follow-up question is, I was more interested in multi-homed EVPN. It's a single device connection to a port over EVPN, or is there multiple devices in EVPN?
So for the time being, we do not have any redundancy in the access. So usually a subscriber, meaning being connected on OLT or MSAN, is only single homed to one leaf switch at the moment. So we are thinking about doing redundancy for business subscribers in the future, but as of now, they are not multi-homed.
Okay. There's a question about software versions. I wonder, from Jordan Santano, I wonder how you ensure the software version of each component of the stack is up to date. Are you using an open source solution to maintain the software components, or a commercial tool from a vendor or various vendors?
Yeah, the point is, as I explained, we do have a central component running on a Kubernetes cluster within the pod. which we call PAO, Port Access Orchestrator. And that component keeps track of all the software versions and, if necessary, initiates the rollout of new software. And this part of software is developed by Deutsche Telekom itself. So this is not an open source project right now.
Okay. Okay. Looks like there's one more question from Matt Petak. If you have Prometheus running on each device to collect and graph the stats, do you have a system for pulling that data from the individual switches back into a central dashboard or dashboard/monitoring system?
Maybe I can take that. Basically, the idea is that the high resolution data actually stays on the switch, right? But there is actually a centralized instance of Prometheus which actually takes the sampled down version of those time series, such that you have got some scaling benefits.
Okay, great. Another question just came in from Boris Kasanov. Do you use any kind of TE between the fabric and the backbone, such as SRTE?
As much as we would love the technology, right? Actually, just adding bandwidth is the easier thing, and essentially within the fabric, bandwidth almost comes for free, right? No, right now we don't use TE.
There was a OLT multi-homing. Was that an answer? Okay, that was your answer to a question about PIM SSM. For PIM, do you use PIM SSM?
Right. Yes, we're using specific multicast. Right.
Okay. Okay. If there are there first off, are there any other questions? And give it a few seconds. I don't see any more questions in the queue. Actually, hold off. I just saw a question pop up from Sanjay Kumar Pangonkar. I hope I got your pronunciation properly. Are you using BNG and router software development by different vendors, or are you using something else?
I didn't get the question completely.
Yes.
Whether the BNG software and the routing software is from different vendors?
No, not at the moment. So right now we are using the software from RT-Break.
Excellent. We are out of time, but thank you very much for your presentation and for your time answering questions.